Theorem 9.1. Theorem 9.1. F is differentiable at A implies F is continuous at A. F is continuous at A. Okay, we want to show this. So, proof. What's our definition of F is continuous, differentiable at A? F differentiable at A implies limit x approaches A, f of x minus f of A all over x minus A exists. Well, great, the limit exists, but I don't know what the limit is. I am just going to call it C, whatever C is. Call the limit as C. Okay. Therefore, f of x plus a, oops. Therefore, limit x approaches A, f of x minus f of A over x minus A is equal to C. Therefore, by properties of limits, I know limit x approaches A, f of x minus f of A is equal to limit x approaches A, C times x minus A, which is equal to C times limit x approaches A of x minus A is equal to C times 0 is equal to 0. Therefore, limit x approaches A, f of x is equal to f of A. And well, that is my definition of the function being continuous at A, right? That the limit of x approaches A of f of x exists and it is equal to f of A. Therefore, we have shown that f is differentiable at A implies f is continuous at A. Therefore, f differentiable at A implies f is continuous at A. Now, the other way is not true. We know, we have seen counterexamples to this, right? F is continuous at A does not imply f is differentiable at A. And the standard counterexample that we have seen before, that you all have seen before, is something, something like this, where great, where you have this point A, and this is f of A, right? Then the function is not differentiable at A, even though it is continuous at A, because the limit of the secant lines from the right hand side, the limit is, the secant lines are going to go like this, and from the left hand side the secant lines are going to go like this, right? And so the function is not differentiable at A. Well, that's fine and dandy, we knew that, but how do I make the function not continuous? Can I make the function not continuous, continuous everywhere and not differentiable anywhere? Can I extend it so that it's not differentiable anywhere? Well, the idea is this. Right now, at all the other points except A, the function is continuous but and differentiable, right? Because it's just a smooth edge. What I'm going to do is make it jagged. Okay. Uh, okay. So now it's not differentiable at this point, this point, this point, this point, and this point. Great. It's still differentiable at all the other points. What do we do? Repeat the process. Oops. Okay. Now it's no longer continuous on this interval either, right? It was continuous, sorry, differentiable here. It's no longer differentiable on all of that interval. I have added points. And I can continue doing this process. I keep making it more and more not differentiable. And by doing so, I'm adding more and more points of non-differentiability while maintaining continuous. Of course, I can't make it the way I'm drawing it. I can't have it not differentiable anywhere by while being continuous, because I can't draw infinitely many discontinuity points. But you can see how the process is going to go. So the standard counterexample is called Weierstrass function, which is constructed this way. There are many constructions. This is not the only function, but this is the most common one that you have seen and that you will see.